Hello everyone and welcome back to the channel. Today we are doing max value of an ordered triplet 2, which also happens to be the problem of the day for today. So we'll have a look at three different approaches. The brute force, basically the most simple, the simplest way to solve the problem, that is obviously targeted for complete beginners. Then we look at a wrong approach, which actually leads us to the right idea, to the right approach. And then from this we are going to lead ourselves towards the optimal solution, and then Mazid, we are going to further optimize this particular solution in terms of the space complexity. So let's have a look at what the problem statement says. It says you're given a zero indexed integer array nums, and that's the only thing which you're given: 12 6 1 2 7 and 1 10 3 4 19, so on and so forth. What we need to do is we need to return the maximum value over all triplets of indices. So we need to select three different indices I, j and k such that I is less than j and j is less than k. Right. For example, 12 6 1 or 12 6 2 or maybe 6 1 7, something like that. Right. Now, obviously, what we are doing is they're saying if all such triplets have a negative value, return 0. What does that mean? In order to understand this particular statement, we need to know what does the value over all triplets statement means, right? What does this phrase means? What do we mean by value over all triplets? The value of a triplet of indices I, j, k is equals to nums of I minus nums of j whole multiplied by nums of k. So for example, if I had chosen 12, 6 and 1, that would have meant 12 if I choose I as 0, j as 1 and k as 2. So that would mean 12 minus 6 into 1. So that would be 6. But then again, this is not the maximum value over all triplets. If for example, if I choose 12, 6 and 7, for example, so 12 minus 6 would be 6 and 6 into 7 would be 42. So that's again a much better result. The maximum, however, will be when I choose 0, 2 and 4. So 12 minus 1 is 11, nums I minus nums j is 11 into 7. So 11 into 7, this is the overall highest answer, and you cannot do any better than that, right? So this is the problem which has been given to us. What would be the brute force approach to solve this? Even any beginner can tell you this, right? You just iterate through all the triplets, right? You have 12 6 1 2 7, right? What you do is you iterate through all the possible indices. So 12 6 1, 12 6 2, 12 6 7. Similarly, then you do 6 1 2 and 6 1 7, and then you do 1 2 and 7. So you iterate over all. Why is this 1 to 7 written over here? Let me just 12 6 1, sorry. Yeah, so you iterate over all the complete space, and then you find out what's the best result for you, right? This is I, this is j, this is k. You calculate what is 12 minus 6 multiplied by 1, you calculate what is 6 minus 1 multiplied by 2, and ultimately where you're going to get the best answer. And even this is not the complete space. You could have had this is just 12 6 1 12. Let me show you what the complete space is going to be. We said 12 6 1, 12 6 2, 12 6 7. It could have been 12 1 2 and 12 1 7. Similarly, it could have been 12 2 7 as well, and so on and so forth. So a lot of different possibilities over here, right? And what we are actually having is the maximum answer. This possibility is basically giving us our maximum answer. So the brute force approach would simply be just go iterate through all the possible triplets and find out the maximum, isn't it? Just do everything that you can, do a lot of effort, and find out what the best answer is. But then if you take a look at the constraints, it says 10 to the power 5. And if you're calculating all the triplets, how much time complexity would that be? That would be O of n cube. So again, that there is no way that particular solution is going to be accepted, isn't it? So you need to do something better. Given that the constraints are 10 to the power 5, maybe we are looking at something which is n log n or O of n, something like this. So you need to sort of think your way through and reduce the complexity from O of n cube to O of n. Thing is, how do we actually accomplish this? So let's have a very close look at what the problem wants us to do, right? The problem wants me to find the maximum value over all triplets. So this is basically the structure, right? Nums of I minus nums of j whole multiplied by nums of k, right? So again, what you would realize is that you need to maximize this portion. In order for this whole expression to be as great as possible, you need to maximize the value of nums I minus nums j. How do you do that? You make sure that nums of I is as big as possible and nums of j is as small as possible, isn't it? 10 minus 1 is obviously, it's 9, but 100 minus 1 is 99. And similarly, for example, if it was 100 minus 10, it would have been even greater. It would have been 110. So you need to maximize nums of I and minimize nums of j. Similarly, this whole portion is being multiplied by nums of k. So goes without saying, you want nums of k to be as maximum as it can, right? So one thing which actually came up in my mind was, why don't we do something like this? So we, for this particular test case, 12, 6, 1, 2, 7, let me actually erase all of this. For this particular test case, why don't I do something like this? So I find out the minimum and label it as j. Okay, so this is my nums of j. Then what do I do is I find out the maximum before it, and then I find out the maximum number which is after it. So max number before and then max number which is after it. Makes sense? So it's, again, we're following our intuition at this point totally. The question is saying you need the maximum value over all triplets, and this is the structure which has been given to us. What if I fix nums of j and then find out what's the maximum value before it in order to maximize nums of I? And in order to maximize nums of k, what do? I want to find out the maximum value after the jth index, isn't it? That's something which I'm trying to do. So in a greedy way over here, what I'm getting is 12 obviously is the biggest value before this, and 7 is the biggest value after this jth index. So I do 12 minus 1 into 7, which gives me 77, and then that is the correct answer in this scenario. But if I take the same approach and if I apply it over here, then you would notice that there is one mistake. This is actually the overall minimum number, right? I actually have to ignore this in this scenario and I have to go with 3. Why? Because the overall maximum overall triplets in this scenario is 10 minus 3 into 19. So even though this was the second highest, this was giving me the overall optimal answer. And the scenario could be even more complicated, right? For example, let's think about this. If this is the second highest, in this example which I have written in front of you, you are getting the maximum answer from this particular triplet. So you even have to ignore the second highest and you actually have to go with the third highest. And you don't know, like it could have been the fourth highest or the fifth highest, which gives you the best answer. So how do we now actually accomplish this task, given that it's so complicated? How do I now accomplish this task, right? How do I now maximize the things which need to be maximized and minimize the things which need to be minimized? How do I do this? You see, this wrong idea actually leads us to the right approach. What we are doing, what the main insight over here is that we are fixing j. And if you have figured this out, this question is a piece of cake for you, right? Just think about this. And I need you to focus very, very critically on this part. Let's say I'm standing at 1. Okay, let's say that this is my j. If I'm standing here at 1, what do I need to know? I need to know the maximum number which is before this j and the maximum number which is after this j, right? That's what we are doing. But the thing is, you see, I don't know where to fix my j. It could be the highest, it could be the lowest number, it could be the second lowest number, but it could very well be the third or fourth lowest number, right? So I don't know where to fix my j. How do I solve this problem? Just take a moment over here, take a break, and think about this. How do I solve this problem? A very simple solution for this is, you see, don't fix j, let j be every possible number. You see what I'm trying to say? So just think about this. When you're standing at any particular number, whether it's 1, whether it's 6, or whether it's 2, what do you need to know? You need to know the maximum number before that particular number, and you want to know the maximum number which is after that particular number, isn't it? So why don't I, have two arrays and I populate them something like this? So the maximum before number, if I'm standing at 1, I want to know what is the maximum number before 1. So I take 12 over here. If 12 greater than 6, no, 12, 12, 12. So no matter where I'm standing, even if I'm standing over here, I know that the greatest number before this index is 12. And I know this for each and every number. I know this for 6, I know this for 1, I know this for 2 in just O of 1 time. Isn't it? Why? Because I took this O of n extra space. And similarly, what I'm going to do is I'm going to populate the maximum after array as well. So over here, the number is 7. Again, the greatest is 7 till here. Till this index, the greatest is 7. Till this index, the greatest is 7. At this point, the greatest becomes 12. So if I'm standing, for example, at 1, I can very easily find out what is the maximum number which is before this index, which is 12, and what is the maximum number which is after this index, which is 7. Isn't it? It's as simple as that. As simple as that. And since I actually, I took this extra space, that is optimizing things a lot for me. Even though I took O of an extra space, I needed these two arrays, but it's giving me a very good optimization in terms of the time complexity. Because when you think about it, when you think about the structure, when you want to, I minus j into k, you want this structure, right? So if you fix j, what do you need? You want to know the maximum number before the jth index and the maximum number which is after the jth index, right? So you are simply doing that over here, nothing else, right? So let's have a look at how we can code this solution up. So yeah, just think about this, right? You want to, for each and every number, for 10, for 3, for 4, for each and every number, you want to know what is the maximum before it and what is the maximum after it. So why don't I track the maximums like this? So for 1, obviously it's going to be 1. Now for 10, 10, for 3 again 10, because 3 is not greater than 10, right? So what I'm basically doing is I'm finding out the prefix max array, isn't it? The prefix max array. Over here it's going to be 10, over here it's going to be 19, because obviously 19 is greater than 10. Similarly afterwards, so I take 19, this is actually the suffix max array. Okay, this is the suffix max array, and I'm letting you know these technical names so that you can explore these concepts on your own as well. I don't want you to sort of just take this as a buzzword. That's why I didn't mention these concepts before. I mentioned them after we, intuitively built up the concept. So, calculating the suffix max array would be 19, because obviously 19 is the greatest of all time number, right? It's the GOAT number. So, yeah. And the overall, when do I get the best answer? I get the best answer when I fix my j at 3. So I'll sort of continue iterating over j. I'll see if 1 gives me the best answer. No, it doesn't. If 10 gives me the best answer, if I fix j at 10, does that give me the best answer? It doesn't. But then when I fix j at 3, it gives me the best answer. Why? Because the greatest number which is before 3 is 10, and the greatest number which is after 3 is 19. You see? So you take 3, you take the greatest number before it, you take the greatest number which is after it, and you calculate what? You calculate nums of I minus nums of j, and this whole expression multiplied by nums of k, right? So yeah, I've actually written a pretty bad code over here. It's not, you not actually bad, but it's what we'll do is we'll actually make it more clean. So the first thing which we need to know, and it's obviously a standard practice, is you just store the value of num size in a separate variable. Then I want two different arrays. So before array, which is also going to be of size n, and the after array, which is also going to be of size n. These are basically my prefix max and my suffix max arrays. Then what do I need to do? How am I going to populate the before and after arrays, right? So let's do something like this. For int I equals 0, I is less than n, I plus plus. If you think about it, you're never going to actually take either the, either the first index or the last index as j. Why? Because you want a number, you want k and you want I. You won't fix j as the very first number, because if you do, then how are you going to select I? Similarly, you are not going to fix j as the last number, because if you do, then how you're going to get k? Because we know that this is the scenario, right? K must be greater than j and j must be greater than I. So this is basically your possible range in order to select j. And then if you put j over here, you can take, for example, this number and this number, so on and so forth. Right. So I actually don't need to start over here from 0. What I can do is I can start from 1. Okay. All right. So the before array, how am I going to populate it? I'm just going to say before of I is going to be the max. Max of what? It's going to be the max of the number which is before it. Okay. Or nums of I minus 1. Just take a moment and I want you to think about what this means. It's as simple as it gets. Just think about it, what it means. You see, your I is at this point, isn't it? Your I is at this point. So what number would you like to put over here? What number would you like to put over here? Would it be 1 or would it be 10? It's obviously going to be either one of. So for 1, let's say we have 1 over here. But then 10 is greater than 1, right? So I calculate the maximum of this and this, and it comes out to be 10. Similarly, when my I is over here, I calculate the maximum of this and this, comes out to be 10. Increment my I calculate the maximum of this and this, again comes out to be 10. I increment my I, and then I want to calculate the maximum of this and this, because this is before of I minus 1, isn't it? And then this is nums of I minus 1. So when you calculate the maximum, it comes out to be 19. Does that make sense? Or maybe think of it this way. So let's literally do what I'm doing over here. Okay. What I'm doing is I'm comparing the max. In order to write something over here, what I'm doing is I'm comparing before of I minus 1, which means whatever is over here, and nums of I minus 1, whatever is over here. So what is the maximum in both these scenarios? It's going to be 10, because I don't actually have anything over here, right? Similarly, I increment my I, then I compare nums of I minus 1 and before of I minus 1. My I is at this point, right? Before of I minus 1 is 10, nums of I minus 1 is also 10, so 10 is going to come over here. Similarly, I increment my what do I compare between? I compare between 3 and I compare between 10. Which is the greater number? 10. So I write 10 over here. Similarly, when I increment my I do this. Out of 4 and 10, which is the greater number? 10 is the greater number. So I'm going to write 10 over here. Okay. This lets me know that at index I, before index I, 10 is the greatest number. The way I originally solved this problem was a bit different, but then now we are actually cleaning the code up a bit. Similarly, for how are we going to calculate the right max? We are going to calculate the right max such that for I need to know what is the maximum number which is after 4. So over here, what am I going to write? I'm going to write 19. Why? Because that is the greater number of 4 and 19. So how I can do that is pretty simple. After of what? After of n minus I minus 1. what does this mean? Which index am I talking about? You see, n minus I means n minus 1, which is this particular number, and then minus 1, so that means I'm talking about this particular place. You see, so it's going to be the maximum of what? It's going to be the maximum of after of n minus I and nums of n minus I. You get my point? So in order to fill up this position, which two numbers do I want to, which two numbers do I want to compare? This and this. Since there is nothing over here, I'm just going to write it over here. And similarly, 19, 19, 19. So that way I basically know that in order, for example, if I fix my j over here, I know that before 3, 10 is the greatest number, and after 3, 19 is the greatest number. Okay, now the question becomes very simple. I just take a variable ans, and then I just iterate from from 1 to n minus 1, and I keep incrementing my I, and I just calculate what the overall maximum answer is. Okay, something like this. So left or uh, before of I minus nums of I, and this whole thing I want to multiply it by not nums of k, after of k, right? I want to multiply it by after of k, and then I need to return my answer. The only thing is that since we are working in long, so I will have to typecast it over here, something like this. So if I now run our code, let's see if it passes all the test cases. No, it does not. Why? Because oh, sorry, I forgot to put brackets over here. Yeah, compiler. Why? Vector of int does not provide a call. What's wrong? What's wrong? Oh, I actually mistakenly used round brackets. Why am I having so many different errors? After of I, sorry. So it passes all the test cases, and then if I run this code, let's see if it overall passes the solution, and it does, right? So if we take a look at our approach, what we are doing is we are taking O of n extra space, but then the good thing is that we were able to reduce our time complexity from O of n cube to literally O of n, right? So I hope you enjoyed the video, and I'm just going to give you a hint. You know what? You can actually solve this problem in O of 1 constant, in O of 1 extra space as well, without taking these two arrays. So if you're really interested, do explore that strategy as well. All right, and I'll see you inshallah in the next one. Take care.